The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start. So last lecture, we started with the strategy of using perturbation theory to study our statistical fields. For example, we would need to evaluate the partition function by integrating over all configurations of a field, let's say n components in d dimensions, with some kind of a weight that we can write as e to the minus beta h. And the strategy of perturbation was to find part of this Hamiltonian that we can calculate exactly, and the rest of it hopefully treating as a small quantity and doing perturbative calculations. Now, in the context of the Landau-Ginzburg theory that we wrote down, this beta h0 was best described in terms of Fourier modes. So basically, we could make a change of variables to integrate over all configurations of Fourier modes, and the same breakdown of the weight in the language of Fourier modes. Since the underlying theories that we were writing had translational symmetry, every point in space was the same as any other, the decomposition into modes was immediately accomplished by going to Fourier representation, and each component of each q value would correspond to essentially an independent weight that we could expand in some power series in this parameter q, which is an inverse of the wavelength, and the lowest order terms are what determines the longer and longer wavelengths. And so there is some m of q squared characterizing this part of the Hamiltonian. And since in real space we had emphasized some form of locality, the interaction part in real space could be written simply in terms of a power series, let's say in M, which means that if we were to then go to Fourier space, things that are local in real space become non-local in Fourier space, and the first of those two terms that we treated as a perturbation would involve an integral over 4 factors of m tilde. Again, translational invariance forces the 4 q's that appear in the multiplication to add up to 0. So I would have m of q1 dot producted with m of q2, m of q3 dot product with m of q4, which is minus q1, minus q2, minus q3. And I can go on and do high order. Okay? So once we did this, we could calculate various, let's say, 2-point correlation functions, etc., in perturbation theory. And in particular, the 2-point correlation function was related to the susceptibility, and setting q to 0, we found an expression for the inverse susceptibility where the 0th order just comes from the t that we have over here. And because of this perturbation calculated to order of u, we had 4u n plus 2, an integral over modes of just the variance of the modes, if you like. Okay. Now, first thing that we noted was that the location of the point at which the susceptibility vanishes, or susceptibility diverges, or its inverse vanishes, is no longer at t equals to 0, but we can see just setting this expression to 0 that we have a Tc, which is minus 4u n plus 2 integral d dk 2 pi to the d 1 over, let's put the k here, k squared potentially higher order terms. Now, this is an integral that in dimensions above 2, let's for time being focus on dimensions above 2, there is no singularity as k goes to 0. K goes to 0, which is long wavelength, is well behaved. The integral could potentially be singular if I were allowed to go all the way to infinity, but I don't go all the way to infinity. All of my theories have an underlying short wavelength, and hence there is a maximum in these Fourier modes, which would render this completely well-behaved integral. In fact, if I forget higher order terms, I could put them, but if I forget them, I can evaluate what this correction Tc is. It is minus 4u n plus 2 over k. This I will write in spherical symmetry as surface area of a d-dimensional unit sphere divided by 2 pi to the d. And then I have the integral of k to the d minus 3, which integrates to lambda to the d minus 2 divided by d minus 2. I wrote that explicitly because we are going to encounter this combination a lot of times, and so we will give it a name, k sub d. So it's just a solid area, solid angle in d dimensions divided by 2 pi to the t. Okay, so essentially in dimensions greater than 2, nothing much happens. There is a shift in the location of the singularity compared to the Gaussian, because you are no longer at the Gaussian, you are at a theory that has additional stabilizing terms such as m to the 4th, etc. So there is no problem now for t going to negative values. The thing that was more interesting was that when we looked at what happens in the vicinity of this new Tc, and to lowest order, we got this form of a divergence. And then at the next order, I had a correction, again coming from this form, 4u n plus 2, an integral. And actually, this was obtained by taking the difference of two of these factors evaluated at t and tc. That's what gave me the t minus tc outside. And then I had an integral that involved two of these factors. Presumably to be consistent to lowest order, I have to evaluate them as small as I can. And so I would have two factors of k squared or k squared plus something. Okay? Presumably higher order terms. The thing about these integrals, as opposed to the previous one, is that, again, I can try to look at the behavior at large k and small k. At large k, no matter how many terms I add to this series, ultimately I will be concerned by cutting it off by lambda. Whereas if I have something that I have set t equals to 0 in both of these denominator factors, I now have a singularity at k goes to 0 in dimensions less than 4. The integral would blow up in dimensions less than 4 if I'm allowed to go all the way to 0, which is arbitrarily long wavelengths. Now, in principle, if I'm not exactly at Tc and I'm looking at singularities being away from Tc, I expect on physical grounds that fluctuations will persist up to some correlation length. So the shortest value of k that I should really physically be able to go to, irrespective of how careful or careless I am with the factors of t and t minus tc that I put here, is of the order of the physical correlation length. And as we saw, this means that there is a correction that is of the form of u k to the k squared c to the power of 4 minus d. And I emphasized that the dimensionless combination of the parameter u that potentially can be added as a correction to a number of order of 1 is uk squared divided by some, multiplied by some length scale to the power of 4 minus d. Above 4 dimensions, the integral is convergent at small values, and the integral will be dominated, and the length scale that would appear here would be some kind of a short distance cutoff, like the averaging length. Whereas in 4 dimensions, the divergence of the correlation length is the thing that will lead this perturbation theory to be kind of difficult and meaningless. Okay? So this is an example of a divergent perturbation theory. So what we are going to do in order to be able to make sense out of it and see how this divergence here can be translated to a change in exponent, which is what we are physically expecting to occur, we reorganize this perturbation theory in a conceptual way that is helped by this perturbative renormalization group approach. So we keep the perturbation theory, but change the way that we look at perturbation theory by appealing to renormalization. Okay? So you can see that throughout doing this perturbation theory, I end up having to do integrals over modes that are defined in the space of the Fourier parameter Q. And a nice way to implement this coarse graining that has led to this field theory is to imagine that this integration is over some sphere where the maximum inverse wavelength that is allowed, or in Q number that is allowed, is some lambda. And so the task that I have on the first line is to integrate over all modes that live in this. And just on physical grounds, we don't expect to get any singularities from the modes that are at the edge. We expect to get singularities by considering what's going on at long wavelengths or 0Q. So the idea of renormalization group was to follow 3 steps. The first step was to do coarse graining, which was to take whatever your shortest wavelength was, make it b times larger and average. That's in real space. In Fourier space, what that amounts to is to get rid of all of the variations and frequencies that are up to lambda over b. Okay? So what I can do is to say that I had a whole bunch of modes, m of q. I'm going to subdivide them into 2 classes. I will have the modes sigma of q. Maybe I will write it in a different color, sigma of q. That are the ones that are sitting here. So these are the sigmas. And these correspond to wave numbers that are between lambda over v and lambda. And I will have a bunch of other variables that I will call m tilde. And these live close to the singularity, but now removed by an amount lambda over v. Okay? So essentially, getting rid of the picture which has fluctuations at short length scale amounts to integrating over Fourier modes that represent your field that lie in this interval. Okay? So I want to do that as an operation that is performed, let's say, at the level of the partition function. So I can say that my original integration can be broken up into integration over this m tilde and the integration over sigma. So that's just rewriting that rightmost integral up there. Okay. And then I have a weight exponential. Okay, let's write it out explicitly. So the weight is composed of beta h0 and the u. Now we note that the beta h0 part, just as we did already for the case of the Gaussian, does not mix up these two classes of modes. So I can write that part as an integral from 0 to lambda over b dd 2 pi over d. And these are things that are really inside, so I could also label them by q lesser. So I have m tilde of q lesser squared. And this multiplies t plus k q lesser squared and so forth over 2. I have a similar term, which is the modes that are between lambda over b and lambda. So I just simply changed or broke my overall integration in beta h0 into two parts. Now I have the higher q numbers, and these are sigma of q larger squared. Again, same weight, t plus k q larger squared and so forth over 2. Make sure this minus is in line with this. And then I have, of course, the u. So then I have a minus u. Now I won't write this explicitly. I will write it explicitly on the next board. But clearly, implicitly, it involves both m tilde and sigma mixed up into each other. Right? So I have just rewritten my partition function after subdividing it into these two classes of modes and just hiding all of the complexity in this function that mixes the two. Okay? So let's rewrite this. I have the integral over the modes that I would like to keep. The m tilde I would like to keep. And there is a weight associated with them that will therefore not be integrated. This is the integral from 0 to lambda over b dd k lesser 2 pi to the d t plus k lesser q lesser squared, etc. and then I have m tilde of q lesser squared. Okay? Now, if I didn't have this term, the u, I could immediately perform the Gaussian integrals over sigmas. Indeed, we already did this, and the answer would be e to the minus. There are n components to this vector, so the answer is going to be multiplied by n. 1/2 is because the square root that I get from each mode. I get the factor of volume integral d dq larger, 2 pi to the d, integrated from lambda over v to lambda, log of t plus k, q greater squared, and so forth. Right? So if I didn't have the u, this would be the answer for doing the Gaussian integration. But I have the u, so what should I do? The answer is very simple. I write it as e to the minus u m tilde and sigma averaged. Okay? So what I have done is to say that with this weight, that is a Gaussian weight for sigma, I average the function e to the minus u. So if you like, this is a Gaussian sigma. So to sort of write it explicitly, what I have stated is an average where I integrate out the high frequency short wavelength modes is by definition integrate over all configurations of sigma with the Gaussian weight, whatever object you have, and then normalize by the Gaussian weight. Of course, in our case, our O depends both on sigma and m tilde, so the result of this averaging will be a function of m tilde, and indeed, I can write this as an integral over m tilde of q with a new weight, e to the minus beta h tilde, which only depends on m tilde because I got rid of and I integrated over the sigmas. And by definition, my beta h tilde that depends only on m tildes has a part that is the integral from 0 to lambda over b, dd q lesser 2 pi to the d, the Gaussian weight, okay, over the range of modes that are allowed. There is a part that is just this constant term. When I take, if I write it in this fashion, there is an overall constant. Clearly what this constant is the free energy of the modes that I have integrated, assuming that they are Gaussian in this interval. The answer is proportional to volume. But as usual, when we are thinking about weights and probabilities, overall constants don't matter. But I can certainly continue to write that over here. So that part went to here. This part went to here. And so the only part that is left is minus log of e to the minus u of m tilde and sigma after I get rid of the sigmas. Okay. so far, I have done things that are extremely general. But now I note that I'm interested in doing perturbation. So the only place that I haven't really evaluated things is where this u is appearing inside the exponential log average, etc. So what I can do is I can perturbatively expand this exponential over here. So I will get log of 1 minus u, which is approximately minus u. So the first term here would be u averaged Gaussian. The next term will be minus 1/2 u squared average minus u average squared, and so forth. So you can see that the variance appears in this stage. And generally, the Lth term in the series would be minus 1 to the L divided by L factorial. And we saw this already. The log of e to the something is the generator of cumulants. So this would be the Lth power of u, the cumulant here would appear. And again, the cumulant would serve the function of cutting off connected pieces, as we shall see shortly. Okay? So that's what we are going to do. We are going to insert the u's, all things that go beyond the Gaussian, but initially just the m to the 4th part, inside this series, and term by term calculate the corrections to this weight that we get after we integrate out the long wave, the long lambda, or the short wavelength modes or the long Q modes. Okay? So let's focus on this first term. So what is this u that depends on both m tilde and sigma? And okay, and I have the expression for u up there. So I can write it as u integral ddq1, ddq2, ddq3 to be symmetric in all of the 4 q's. I write an integration over the 4th q, but then enforce it by a delta function that the sum of the q's should be 0. Okay? And then I have 4 factors of m, but an m, depending on which part of the Q space I am encountering, is either a sigma or an m tilde. So without doing anything wrong, I can replace each m with an m tilde plus sigma. So depending on where my Q1 is in the integrations from 0 to lambda, I will be encountering either this or this. And then I have the dot product of that with m tilde Q2 plus sigma of Q2. And then I have the dot product that would correspond to m tilde of Q3 plus sigma of Q3 with m tilde of Q4 plus sigma of Q4. Okay? So that's the structure of my U. Okay? And again, what I have to do in principle is to integrate out the sigmas, keeping the m tildes when I perform this averaging over here. Right? So let's write down, if I were to expand this thing before the integration, what are the types of terms that I would get? And I'll give them names. One type of term that is very easy is when I have m tilde of q1 dotted with m tilde of q2, m tilde of q3 dotted with m tilde of q4. If I expand this, so there's 2 terms per bracket, and there are 4 brackets, so there are 16 terms. Only one of these terms is of this variety out of the 16. What I will do is also now introduce a diagrammatic representation. Whenever I see an m tilde, I will include a straight line. Whenever I see a sigma, I will include a wavy line. So this entity that I have over here is composed of 4 of these straight lines. And I will indicate that by this diagram, Q1, Q2, Q3, Q4. And the reason is, of course, first of all, there are 4 of these. So this is a so-called vertex in a diagrammatic representation that has 4 lines. And secondly, the lines are not all totally equivalent because of the way that the dot products are arranged. Say Q1 and Q2 that are dot producted together are distinct, let's say, from Q1 and Q3 that are not dot producted together. And to indicate that, I make sure that there is this dotted line in the vortex that separates and indicates which 2 are dot producted to each other. Okay? Now, the second class of diagram comes when I replace one of the m tildes with a sigma. So I have sigma of Q1 dotted with m tilde of Q2, m tilde of Q3 dotted with m tilde of Q4. Now, clearly in this case, I had a choice of 4 factors of m tilde to replace with this. So of the 16 terms in this expansion, 4 of them belong to this class, which if I were to represent diagrammatically, I would have one of the legs replaced with a wavy line and all the other legs staying as solid lines. Okay. The third class of terms correspond to replacing 2 of the m tildes with sigmas. Now here again I have a choice whether the second one is a partner of the first one that became sigma, such as this one, sigma of Q1 dotted with sigma of Q2, and tilde of Q3 dotted with m tilde of Q4. And then clearly I could have chosen one pair or the other pair to change into sigmas. So there are 2 terms that are like this. And diagrammatically, the wavy lines belong to the same branch of this object. Okay, next, keep going. Actually, I have another thing when I replace 2 of the m tildes with sigma, but now belonging to 2 different elements of this dot product. So I could have sigma of Q1 dotted with m tilde of Q2, and then I have sigma of Q3 dotted with m tilde of Q4. In which case, in each of the pairs, I had a choice of 2 for replacing m tilde with sigma. So that's 2 times 2. There are 4 terms that have this character. And if I were to represent them diagrammatically, I would need to put two wavy lines on two different branches. And then I have the possibility of three things replaced. So I have sigma of Q1, sigma of Q2, sigma of Q3, m tilde of Q4. And again, now it's the other way around. One term is left out of 4 to be m tilde. So this is again the degeneracy of 4. And diagrammatically, I have three lines that are wavy and one line that is solid. And the end of the story, 6, I will have one diagram which is all sigmas. Which can be represented essentially by all wavelengths. Okay. And to check that I didn't make any mistake in my calculation, the sum of these numbers better be 16, so that's 5, 7, 11, 15, 16. All right? Now, the next step of the story is to do these averages, right? So I have to do the average. Okay. Now the first term doesn't involve any sigmas. All of my averages here are obtained by integrating over sigmas. If there is no sigmas to integrate, after I do the averaging here, I essentially get the same thing back, right? So I will get this same expression. And clearly, that would be a term that would contribute to my beta H tilde, which is identical to what I had originally. It is again m to the 4th. So that we understand. Now the second term here, what is the average that I have to do here? Okay, I have one factor of sigma with which I can average, but the weight that I have is even in sigma. So the average of sigma, which is Gaussian distributed, is 0. So this will give me 0. Okay? And clearly, here also, there is a term that involves 3 factors of sigma. Again, by symmetry, this will average up to 0. Okay? Now, there is a way of indicating what happens here. See, what happens here is that I will have to do an average of this thing. The m tildes are not part of the averaging. They just go out. The average moves all the way over here, right? And the average of sigma of Q1, sigma of Q2, I know what it is. It is going to be, I could have just written it over here. It's a 2 pi to the d delta function Q1 plus Q2 divided by kq squared. Maybe I'll explicitly write it over here. So what we have here is that the average of sigma of Q1 with some index, sigma of Q2 with some other index, is, first of all, the two indices have to be the same. I have a delta function Q1 plus Q2, and then I have t plus k Q1 squared, and so forth. Right? So it's my usual Gaussian. So essentially, you can see that one immediate consequence of this averaging is that previously these things had two different momenta and potentially two different indices. they get to be the same thing. And the fact that the labels that were assigned to this, the Q and the index alpha, are forced to be the same, we can diagrammatically indicate by making this a closed line. So we are going to represent the result of that averaging with essentially taking these two lines are unchanged. They can be whatever they were. These two lines really are joined together through this process. So we indicate them that way. And similarly, when I do the same thing over here, I do the averaging of this, and the answer I can indicate by leaving these two lines by themselves and joining these two wavy lines together in this fashion. Okay? Now, when you do this one, we said is 0, so there's essentially 1 that is left, which is number 6. For number 6, we do our averaging. And for that, we have to use, for average of a product of 4 sigmas that are Gaussian distributed, Wick's theorem. So one possibility is that sigma 1 and sigma 2 are joined, and then sigma 4 and sigma 3 have to be joined. So basically, I took sigma 1 and sigma 2 and joined them, sigma 3 and sigma 4 that I joined them. But another possibility is I can take sigma 1 with sigma 3 or sigma 4. So there are really two choices. And then I will have a diagram that is like this. Okay. Now, each one of these operations and diagrams really stands for some integration and result. And let's, for example, pick our number 3. For number 3, what we are supposed to do is to do the integration. First of all, number 3 has a numerical factor of 2. This is something that is proportional to u when we take the average. I have, in principle, to do integration over q1, q2, q3, q4. Okay. The m tilde of q3 and m tilde of q4 in this diagram were not averaged over, so that term remains. I did the averaging over q1 and q2. When I did that averaging, I first of all got a delta alpha alpha, because those were two things that were dot producted to each other, so they were carrying the same index to start with. I have a 2 pi to the d, a delta function q1 plus q2, and I have t plus k q1 squared plus. Okay. Now delta alpha alpha summing over alpha gives a factor of n. And when you look at these diagrams, quite generally, whenever you see a loop, with a loop, you would associate the factor of n because of the index that runs and gets summed over. So this answer is going to be proportional to 2un. Now, q1 and q2 are said to be 0, the sum. So this is 0. So Q3 and Q4 have to add up to 0. So the part that involves Q3 and Q4, the m tilde, essentially I will get an integral dd, let's say whatever Q3, doesn't matter because it's an index of integration. I have m tilde of Q3 squared. And again, Q3, it is something that goes with one of these m tildes. So this is an integration that I have to do between 0 and lambda over b. Okay? So there is essentially one integration left because Q1 and Q2 are left to be the same. So this is an integral, let's call the integration variable that was Q1, I could call k, doesn't matter, 2 pi to the d, the same integral that we've seen before. Except that since this originated from the sigmas, the integration here is from lambda over b to lambda. Okay? So this is basically a number that I can take, say, out here and regard as a coefficient that multiplies a term that is m tilde squared. And similarly, 4, we said we have 4 diagrams of this variety, so this would be a contribution that is 4u. I can write out the whole thing. Certainly, I have all of this. I have all of this. In that case, I have m tilde Q3, m tilde, well, let's see. I have m tilde of Q2, m tilde of Q4, and they carry different indices because they came from 2 different dot products. And then I have to do an average over sigma 1 and sigma 3, which carry different indices, delta, alpha, beta, 2 pi to the d, delta function Q1 plus Q3, P plus K, Q1 squared, Q1 squared, and so on. Again, since Q1 plus Q3 is 0 and the sum of the 4 Q's is 0, these two have to add up to 0. So the answer can be written again as 4u integral 0 to lambda over b, dd of some q divided by 2 pi to the d, m tilde of q squared, and then actually the same integration, lambda over b, lambda ddk, 2 pi to the d, 1 over t plus k squared. Okay. So out of the 6 terms, 2 are 0. 2 are explicitly calculated over here. 1 is trivially just m to the 4th. The last one is basically summing up all of these things. But these explicitly do not depend on m tilde. So I'll just call the result of doing all of this some v delta fv at level 1. In the same way that integrating the modes sigma that I'm not interested and averaging over them gave a constant of integration, that constant of integration gets corrected to order of u over here. I don't need to explicitly take care of it. Okay? So given all of this information, let's write down what our last line from the previous board is. So our intent was to calculate a weight that governed these coarse-grained modes. And our answer is that, first of all, we will get a bunch of constants, delta fb0 plus delta fb1 but we don't really care. They're just an overall change in that doesn't matter for the probabilities. It's just contribution to the free energy. And then we start to get things, and to the lowest order what we had was replacing the Gaussian weight, but only over this permitted set of wavelengths. So I have dD q lesser, let's say 2 pi to the d, t plus k q lesser squared and so forth, divided by 2 m tilde of q squared. Okay? Then term number 1 in the series gave me what? It gave me something that was equivalent to my u, if I were to Fourier transform back to real space, m to the 4th, except that my cutoff has been shifted by lambda over b. So I don't want to bother to write down that full form in terms of Fourier modes. Essentially, if I want to write this explicitly, it is just like that line that I have, except that for the integrations, I have to explicitly indicate 0 to lambda over b. Okay? All right, so the only terms that we haven't included are the ones that are over here. Now you look at those terms, and you find that the structure of these terms is precisely what we have over here, right? Except that there is a modification. There is a constant term that is added from this one, and there's a constant term that is added from that one. So the effect of those things I can capture by changing the parameter t to something else, t tilde. So you can see that to order of u squared that I haven't calculated, to order of u, the only effect of this coarse graining is to modify this one parameter so that t goes to t tilde, which certainly depends on how much I coarse grain things. And this is the original t plus the sum of these things. So I will have 2 n plus 2 u integral d dk 2 pi to the d 1 over t plus k, k squared, and presumably high order terms are allowed, going from 0 to lambda over t.
Question.
Yes? Question?
Yeah. When you have an integration over x, if you had previously defined lambda to be a cutoff in k space, might it be, is it 1 over b lambda then, or is it b over lambda? Because
Okay. You're right. So previously, maybe the best way to write this would have been that there is a shortest length scale A. So I should really indicate what's happening here as shortest length scale having gone to BA. And there is always a relationship between the A and lambda, which is inverse relation, but there's a factors of 2 pi and things like that, which I don't really want to bother. Doesn't matter. Yes?
Should it be t tilde is equal to t plus 4 multiplied by n?
Exactly, good, because the coefficients here are divided by 2, so that 2 I forgot, and I should restore over here. And if I had gone a little bit further, I would have then started comparing this formula with this formula, and I realized that I should have had the 4. Clearly, the two formulas are telling me the same thing. You can see that they are almost exactly the same, with the exception of how much integration I'm doing. Yes?
So one of the things, are the bounds in this integral for your t, b, should they be lambda over e to lambda?
Yes. Lambda over b to lambda. And it is because of that that I don't really have to worry, because we saw that when we were doing straightforward perturbation theory, the reason that perturbation theory was blowing up in my face was integrating all the way to the origin, and the trick of renormalization group is by averaging out there, I don't really yet reach this singularity that I would have at k equals to 0. This integral by itself is not problematic at k goes to 0, but future integrals will. Okay? Any other mistakes? No. All right. So, but the other part of the story is that the effect of this coarse graining at lowest order in U was to modify this parameter t, but importantly to do nothing else. That is, we can see that in this Hamiltonian that we had written, the k that is rescaled is the same as the old k, and the u is the same as the old u. That is, to the lowest order, the only effect of coarse graining was to modify the parameter that couples coefficient of t squared. Okay? But we have not completed our task of constructing a renormalization group. The renormalization group had 3 steps. The most difficult step, which was the coarse graining, we have completed, but now we have generated a grainy picture in which the shortest wavelengths are a factor of b larger than what we had before. In order to make our pictures look the same, we had to do steps 2 and 3 of RG. Step 2 was to shrink all of the lengths in real space, which amounts to q prime being b times q. And that will restore the upper cutoff of the q integration to be lambda. And there was a rescaling that we had to perform for the magnitude of the fluctuations, which amounted to replacing the m tilde of q with z m prime. So this would be, if you like, q lesser, and this would be m prime. Okay. Now the reason these steps are trivial is because just whenever I see a q, I replace it with b inverse q prime. Whenever I see an m tilde, I replace it with z m prime. So then I will find a Hamiltonian that characterizes the m prime variables, the RG implemented variables, which is, okay, there's a bunch of constants up front. Delta ft, actually it's 0 u delta ft1. And in the sign I had to put as plus, but really it doesn't matter. And then I go and write down what I have. The integration over q prime after the rescaling is performed goes back to the same cutoff or the same shortest wavelength as before, except that when I do this replacement of q lesser with q prime, I will get a factor of b to the minus d from here. And there are d integrations. And then I have p tilde. The next term is k tilde, but k tilde is the same thing as k. Goes with q squared, so this becomes q prime squared, and then I will get a b to the minus 2. Higher orders will get more factors of b to the minus 2 over 2. And then I have m tilde, which is replaced by z, and there are two of them. I will get m prime of q prime squared. If I were to explicitly now write the factors that go in construction of u, since u had 3 integrations over q, left board over there, I will get 3 integrations over q prime. Giving me a factor of b to the minus 3d. And then I have 4 factors of m tilde that become m prime. Along the way, I will pick up 4 factors of c. And then, of course, order of u squared and so forth. So under this 3 steps of RG, what happened was that I generated t prime, which was z squared b to the minus d is t tilde. I generated u prime, which was z to the 4th b to the minus 3d u, the original u. And I generated a k prime, which was z squared b to the minus d minus 2k. And I could do the same for various other factors. Okay. Now again, we come up with this issue of what to choose for for z. And what I had said previously was that we went through all of this exercise of doing the Gaussian model by RG in order to have an anchoring point. And there we saw that the thing that we were interested was to look at the point where k prime was the same as k. So let's stick with that choice and see what the consequences are. So choose z such that k prime is the same as k, which means that I choose my z to be b to the 1 plus d over 2, exactly as I had done previously for the Gaussian model. So now I can substitute these values and therefore see that following a rescaling by a factor of b, the value of my t prime, z squared b to the minus d, I will get b to the power of 2 plus d minus d, so that would give me my b squared. And I have t plus 4u n plus 2, this integral from lambda over b to lambda, d k 2 pi to the v, 1 over t plus k squared, so forth. Presumably the order of u squared. And that my factor of u rescaled by b, I have to put 4 factors of z. So I will get b to the 4 plus 2d, and then 3d gets subtracted. So I will get d to the 4 minus d and u again, but presumably order of u squared. Okay. So the first factors are precisely the things that we had done and obtained for the Gaussian model. So the only thing that we gained by this exercise so far is this correction to t. We will see that that correction is not that important. And in order to really gain an understanding, we have to go to the next order. But let's use this opportunity to also make some changes of terminology that is useful. So clearly, the way that we had constructed this, and in particular, if you are thinking about averaging over spins, etc., in real space, the natural thing to think about is that maybe your b is a factor of 2 or a factor of 3. You sort of group things by a factor of twice as much and then do the averaging. But when you look at things from the perspective of this momentum shell, this b can be anything. And it turns out to be useful just as a language tool, not as a conceptual tool, to make this b to be very close to 1, so that effectively we are just removing a very, very tiny thin shell around the boundary. Okay? So essentially what I'm saying is choose b that is almost 1, but maybe a little bit shifted from 1. Okay? Then clearly, as b goes to 1, then t prime has to go to t, u prime has to go to u. So what I can do is I can define t prime scaled by a factor of 1 plus delta L to be t plus a small amount dt by dl, and then order of delta L squared. And similarly, I can write u prime to be u plus delta L du by dl and higher order. And the reason is that if we now look at the parameter space, t, u, whatever, the effect of this procedure, rather than being some jump from some point to another point, because we rescale by a factor of b, is to go to a nearby point. So these things, dt by dl, du by dl, essentially point to the direction in which the parameters would change. And so they allow you to replace these jumps that you have by things that are called flows in this parameter space. So basically, you've constructed flows and vectors that describe the flows in this parameter space. Okay? Now, if I do that over here, you can also see some other things emerging. So b squared I can write as 1 plus 2 delta L. And then here I have t. Now clearly here, if b was 1, the integral would be 0. I'm integrating over a tiny shell. So the answer here when b goes to 1 is really just the area of that sphere multiplied by the thickness. And so what do I get? I get 4un plus 2 is just the overall coefficient. Then what is the surface area? I have the solid angle divided by 2 pi to the d. Okay, we divide solid angle divided by 2 pi to the d to be kd. what's the value of the integrand on shell. On shell, I have to replace k with the lambda, so I will get t plus k lambda squared. Actually, the surface area is st lambda to the d minus 1, but then the thickness is lambda delta L. Okay. The second one is actually very easy. It is 1 plus 4 minus d delta L times u. So you can see that if I match things to order of delta L, I get the following RG flows. So the left-hand side is T plus delta L dt by dl. The right-hand side, if I expand, there is a factor of T, so that gets rid of. And I'm left with a term that is proportional to delta L, whose coefficient on the left-hand side is dt by dl. And the right-hand side, I get either a factor of 2t from multiplying the 2 delta L with t, or from multiplying the 1 with the result of this integration, I will get a 4u n plus 2 kd lambda to the d divided by t plus k lambda squared. I don't need to evaluate any integrals. And the second flow equation for the parameter u, du by dl, is 4 minus d u. Okay. Now, clearly, in the language of flows, a fixed point is when there is no flow. So I will have dt by dl, du by dl need to be 0. And du by dl being 0 immediately tells me that u star has to be 0. And if I set u star equals to 0, I will see that t star has to be 0. So these equations have one and only one fixed point at this order. And then looking for relevance and irrelevance of going away from the fixed point can be captured by linearizing. That is, I write my t to be t star plus delta L. Of course, my t star and u star are both 0, but in general, if they were not at 0, I would linearize my, in general, nonlinear RG recursions by going slightly away from the fixed point. And then the linearized form of the equation would say that going away by a small amount delta t, delta u, and there could be more and more of these operators, can be written in terms of a matrix multiplying delta t and delta u. And clearly, the matrix for u is very simple. It is simply proportional to 4 minus d delta u. The matrix for t, well, there's two terms. First of all, there is this 2. And then if I'm taking a derivative, there will be a derivative of this expression because there's a t dependence here. But ultimately, since I'm evaluating it at u star equals to 0, I don't need to include that term here. But if I now make a variation in u, I will get an off-diagonal term here, which is k lambda squared. So these two can be combined to each other. Okay? Now, looking for relevance or irrelevance is then equivalent. Previously, we were talking about it in terms of the full equations with b that could have been anything, but now we have gone to this limit of infinitesimal b. Then what I have to do is to find the eigenvalues of the matrix that I have for these flows. Now, a matrix that has this structure where there's 0 on one side of the diagonal, I immediately know that the eigenvalues are 2 and 4 minus t. So basically, depending on whether I'm in dimensions greater than 4 or less than 4, I will have either 2 or 1 relevant direction. In particular, if I look at what is happening for d that is greater than 4, for d greater than 4, I will just have 1 relevant direction. And if I look at the behavior and the flows that I'm allowed to have in the two parameters t and u. Now, if my Hamiltonian only has t and u, I'm only allowed to look at the case where u is positive in order not to have weights that are unbounded. My fixed point occurs at 0, 0. And then one simple thing is that if u is 0, it will stay 0, and then dt by dl is 2t. So I know that I always have an eigendirection that is along the t and is flowing away with a velocity of 2, if you like. The other eigendirection is not the axis t equals to 0, because if t is 0 originally but u is non-zero, this term will generate some positive amount of t for me. So if I start somewhere on this axis, t will go in the direction of becoming positive. Above 4 dimensions, u will become less. So above 4 dimensions, you can see that the general trend of flows is going to be something like this. Indeed, there has to be a second eigendirection because I'm dealing with a 2 by 2 matrix. And if you look at it carefully, you'll find that the second eigendirection is down here and corresponds to a negative eigenvalue. So I basically would be having flows that go towards that. And in general, the character of the flows, if I have parameters somewhere here, they will be flowing there. If I have parameters somewhere here, they will be flowing there. Okay? So physically, I have something like iron in 5 dimensions, for example, and it corresponds to being somewhere here. And I change the temperature of iron in 5 dimensions, and I execute some trajectory such as this. All of the points that are on this side of the trajectory under flow will go to a place where u becomes small and t becomes positive. So I will essentially go to this Gaussian-like fixed point that describes independent spins. All the things that are down here, which previously in the Gaussian model we could not describe because the Gaussian model did not allow me to go to t negative, because now I have a positive view, I have no problem with that. And I find that essentially I go to large negative t corresponding to some positive u, I can figure out what the amount of magnetization is. And so then in between them, there is a trajectory that separates paramagnetic and ferromagnetic behavior, and clearly that trajectory at long scales corresponds to the fixed point that is simply the gradient squared, because all the other terms went to 0. So we know all of the correlation functions, etc., that we should see in this system. Unfortunately, if I look for d less than 4, what happens is that I still have the same fixed point. And actually, the eigendirections don't change all that much. U equals to 0 is still an eigendirection that has relevance too. But the other direction changes from being irrelevant to being relevant. So I have something like this. And the natural types of flows that I get kind of look like this. And now if I take my iron in 3 dimensions and change its temperature, I go from behavior that is kind of ferromagnetic, paramagnetic-like to ferromagnetic-like, and there is a transition point, but that transition point, I don't know what fixed point it goes to. I have no idea. So the only difference by doing this analysis from what we had done just on the basis of scaling and Gaussian theory, etc., is that we have located the shift in t with u, which is what we had done before. So was it worth it? The answer is, up to here, no, but let's see if we had gone one step further, what would have happened. The series is an alternating series. So the next order term that I get here, I expect will come with some negative u squared. So let's say there will be some amount of work that I have to do, and I calculate something that is minus au squared. I do some amount of work, and I calculate something that is minus bu squared. But then you can see that if I search for the fixed point, I will find another one at u star, which is 4 minus t over b. So I will find another point, and indeed will find that things that left here will go to that point. And so that point has one direction here, it was relevant, that becomes irrelevant, and the other direction is the analog of this direction, which still remains relevant, but with modified exponents. We will figure out what that is. So the next step is to find this p, and then everything will be resolved. The only thing to then realize is, what are we perturbing it? Because the whole idea of perturbation theory is that you should have a small parameter. And if we are perturbing in u, and then basing our results on what is happening here, the location of this fixed point better be small, close to the original one around which I'm perturbing. So what do I have to make small? 4 minus t. So we thought we were making a perturbation in u, but in order to have a small quantity, the only thing that we can do is to stay very close to 4 dimension and make a perturbative expansion around 4 dimension.